All right, at the end of class yesterday, you guys were supposed to have done example 2. We just ran out of time for us to talk about it. So you will have some problems like this. We're going to graph these points, 2, -3, -4, -3, and -4, -7. And you should have a triangle that looks like this drawn on your paper. So how'd I do? Does mine match yours? Does yours look like this?
Yes.
Yeah, correct me if I'm wrong now because this is on film, so I don't want to do something wrong on film. That would be bad. Everything good? All right, so we're going to do what we did on example 1. We're going to find the intersection of the perpendicular bisectors, because this word circumcenter, that is just like example 1, it's the intersection of the perpendicular bisectors. So this is the same kind of question. We're going to find the perpendicular bisectors. And it would be a good idea while you're doing these problems to have this handy, because this tells you all the theorems and what goes with each of these segments and points of concurrency. Did you have a question, Malachi?
Yes, I think I missed that.
Okay. So come grab one. All right, after you get it graphed, sometimes it's graphed for you, sometimes you have to graph it your own self. So after you have it graphed, you're going to find the perpendicular bisectors. So I'm going to find the perpendicular bisector of this segment right here. And this segment is 1, 2, 3, 4, 5, 6 spaces long, right? So you count how long it is. It's 6 spaces. So halfway would be over 3 spaces. So you should have gone over 1, 2, 3 spaces. There's the midpoint. So that's where a bisector would pass through. And it's a perpendicular bisector, so it would be a vertical line to bisect that horizontal line. So that's one of the perpendicular bisectors. And then I'm going to do the same thing to the vertical side over there on the left. So the vertical side over there on the left, it is 1, 2, 3, 4 spaces tall, right? And so to find the middle of it, it would be 2 spaces and 2 spaces. So you're just cutting that segment in half, 2 and 2, and that's where the perpendicular bisector would go. So we'll draw a perpendicular to that side. You're drawing a line perpendicular to that side. And where they cross would be where all 3 of the bisectors would cross. You only have to draw 2 of them. So where 2 of them cross, that's the spot where all 3 would cross. So that's the intersection of those perpendicular bisectors. So that's called the circumcenter. And then you just have to write down what that point is. Starting at the origin, that's the point -1, -1, 2, 3, 4, 5. -1, -5. Make sure I counted right. 1, 2, 3, 4, 5. Yep. All right, so to answer a question about a circumcenter, you perpendicular bisect one side, you perpendicular bisect another side, and wherever those perpendicular bisectors cross, that's your circumcenter. I am only going to ask you to do that with triangles like these right triangles. If it's a different kind of triangle, this process is a little harder. So I'm only going to ask you to do that with these right triangles like this. Okay, questions? So far, so good? Okay, next question. Next question says, name the point of intersection of the angle bisectors. Name the point of intersection of the angle bisectors. So we learned yesterday that's called an incenter. We're looking for the incenter. So you look at the picture and you find the 2 angle bisectors, or all 3 of them if they drew all 3 of them, and you see where they cross. So This right here, since these angles are marked congruent, that's an angle bisector. So that's one of them. That's one angle bisector. Now I need to find the other angle bisector. Now see how these two segments are kind of close together? So you have to look at this real carefully. One of these is an angle bisector, and one of these is not. So the question is, do you know which one of these lines right here, which one of these segments is an angle bisector? Do you know which one?
I think so.
Okay, which one?
I think it's BE.
It is BE.
Okay, and I think that because BD has the little square box next to it,
Yep, which makes it,
the anchor thing.
yep, which is an altitude.
Altitude, yeah.
That's exactly right. So because of that right angle, that thing right there is an altitude. Altitudes come down and make a right angle. So the angle bisector, see, it's a little hard to tell up here because you can't really tell which one is dividing that into the two angles, but this is the other angle bisector right here. So Malachi, that was perfectly explained. Very nice. So where do those two things cross? That's the question. Are they crossing at F or are they crossing at H? What do y'all think? F. Because F is on this side and H is over there. So the point of intersection, the point of concurrency of the angle bisectors is point F. And if they asked, you could tell what that's called. The intersection of the angle bisectors is called the incenter. So F right there would be the center of the circle that's inside that triangle. Yeah, so you find the angle bisectors and see where they cross. All right, example 4. I don't know about you guys, but these pictures, to me, the pictures themselves are a little overwhelming. I don't know if y'all think so, but I think there's a lot going on here. So let's talk about what's going on. It says find the value of x, but let's talk about what's happening with these segments. So see how you have angle marks here, which makes this right here an angle bisector. So I'm going to write that down. That's an angle bisector. And then isn't that also happening over here? Because of those marks, because of these angle marks, that's also an angle bisector. So because of those angle marks, we've got two angle bisectors. And they're meeting, right? They're meeting right here. So that right there, that's an incenter. Because it's where two angle bisectors are crossing. Now, if you get lost or you get stuck, just refer to this. Keep this handy and look at what it says about that. So, angle bisectors cross at an incenter, and then look at what it says is true about them. This is the important part for this problem. That incenter is equidistant from the sides of the triangle. That's the theorem. So there's a theorem about it. It's equidistant from the sides of the triangle. So that incenter right there is an equal distance from the sides of the triangle. That's why they gave you these two distances. This distance is x plus 5. This distance is 3x minus 7, or plus 7.
Oh, sorry.
These are equal distances because that's an incenter. So that incenter, I'm going to write that down over here. The incenter, that's what this is. That's what that point is because it's the angle bisectors, is equidistant from the sides. So that's what's happening in this picture. We've got these two angle bisectors. They're meeting. That point where they meet is the incenter, and that incenter, according to this theorem, and remember, you're going to get to use this. You don't have to memorize these. Not that you can't. I'm not trying to insult your intelligence. I'm just saying you don't have to. Then you'll know that it's equidistant to the side. So that's why these things are equal, because this is a distance to a side, and this is a distance to a side. So x plus 5 is equal to 3x plus 7. And then we have to solve that thing. All right, so you guys solve it if you haven't already. Did y'all get -1? Yeah. So when you subtract x, you get 2x over here. But then you have to subtract 7, so you get 2x equals -2, and divide, you get -1. It's okay to get negatives so long as distances aren't negative. And this distance would be 4, and this distance would be 4. So it's okay to get negative numbers so long as distances aren't negative. And they aren't. It's all good. That negative made me think for a minute, and then I'm like, wait, it's negative. But our distances are positive. Okay, example 5, or question 5. It says, where should the fire station be placed? They're going to place a fire station. And what they've got is a police station, a hospital, and a grocery store. Where should the fire station be placed so that it's equidistant from these 3 things, the grocery store, the hospital, and the police station? Okay, so notice that the grocery store and the hospital and the police station, those are the vertices of the triangle, right? Those are the points of the triangle. And we want our fire station to be equidistant from those vertices. So equidistant from the vertices. So if you look at this little chart, find the one that says equidistant from the vertices. So here you have circumcenter. The circumcenter is equidistant from the vertices. So that's what they're asking us to find. They're asking us to find the circumcenter because that's the thing that's equidistant from the vertices. And so I need to find the perpendicular bisectors. So it doesn't seem like it, but this question is the same question as question number 1 and question number 2. It's the same question. Because equidistant from the vertices is the circumcenter. And the circumcenter comes from the perpendicular bisectors. So it's the same exact question as 1 and 2. All right, so you guys answer that one. Draw those perpendicular bisectors and see where they cross. So to draw the perpendicular bisectors, you need to find the middle of 2 sides. This side is 1, 2, 3, 4, 5, 6 spaces long. So you're going to put the middle right there at 3 and 3. And then it's a perpendicular bisector, so you have to draw a perpendicular. And then you're going to draw another one and see where they cross. And so I'm going to find the perpendicular bisector of this one. It's 1, 2, 3, 4, 5, 6 spaces long. That one's also 6 spaces long. So right in the middle would be 3 and 3. So it would be right here. And you draw it perpendicular. And that is where they cross, right there. So if you put a fire station right there, it's the same distance to the police station, to the grocery store, and to the hospital. That point is the same distance from all of those. And that would be, here's our origin, that would be over 1, up 1. So it's the point 1, 1. That's where the fire station should be at point 1, 1. Anybody in the room want to be a city planner and plan out where things like that go, like fire stations and to be equidistant from large neighborhoods and stuff.
I would like to be the city planner's boss.
Oh, yeah? I think the city planner probably is the boss. I don't think there's a higher up to a city planner.
To the mayor?
Well, our mayor's more of like a figurehead kinda. I don't think he has any real like authority. He runs meetings and stuff, but I think it's the county commissioners and the city commissioners that have authority, maybe. I could be wrong about that. Okay. On the back, we're gonna do these three together, and then you guys are gonna do the rest, okay? Because after we do these three, we've covered it all, and these are just review questions. So, question 1, 2, and 3. This is the most math you'll have to do is involving the median and the centroid, okay? So let's just look at the rule real quick before we do this. So the medians cross at the centroid, and if you remember yesterday, the centroid is that balancing point of the triangle. So it's the point where you could put your finger there and it would balance on there. Medians cross at the centroid, and here's where the math is going to come in. The centroid, that point, is located 2/3 of the distance from the vertex to the midpoint of the opposite side. It's 2/3 of the way. So in other words, this centroid right here divides that median 2/3 and 1/3. And it divides this median 2/3 and 1/3. And it divides this median 2/3 and 1/3. That's what a centroid does. It divides each median into a 2/3 portion and a 1/3 portion. Okay? So let's do math with that. It says CW, this whole thing is 15. The whole thing is 15. But we have to divide it 2/3 and 1/3. So if you have, just in case you have trouble with fractions, I want you to think about this. We're dividing 15 into thirds. So isn't that a 5 and a 5 and a 5, right? If we divide 15 into thirds. So the longer segment is 2 of those thirds, and the shorter segment is 1 of those thirds. So the longer segment is 2/3, which is 10, and the shorter segment is 1/3, which is 5. So you're thinking of the whole segment being divided into thirds. And so CX from here to here, that would have to be 10. And then XW from X to W, the shorter part, that would have to be 5. To make a total of 15. And this is 2 of those thirds, and this is 1 of those thirds. So it would be 10 and 15. Now, you'll notice when you do these problems that the longer part is always double the shorter part. Because it's 2/3 and 1/3, and 2/3 is double 1/3. So that might help you on some of the problems. This longer part is going to be double the shorter part. So then look at the next one. Oh, this would be, hold on, let me write that down. This would be 10 and 5. Okay, let's look at this one. They gave you BX. They gave you this right here is 8. See, they're not giving you the whole thing. They're giving you from B to X. And that's the 2/3 part. This is the 1/3 part. So when you start the vertex, that gives you the 2/3 part. So if this part's 8, how long is this part? 4. Because if the 2/3 part is 8, the 1/3 part is 4. And the whole thing is 12. So BY, that's the whole thing, is the 8 and the 4 together, that's 12. And XY, that short part, is 4. So what's happening on that one is the 12 is the whole thing, and 12 is 4 and 4 and 4. That's how to divide it into thirds. And so the 2/3 portion was 8, and the 1/3 portion was 4. So that's what's happening on that one. All right, the last one, they gave us They gave us XZ. So they're giving us the short one, and that is 3. So that, I can't write that small. 3. Okay, so if the short one is 3, and that's the 1/3 part, how long is this longer part? If the short part is 3, it is 6. And the whole thing's 9. So A to X is 6, and A to Z is 9. So here's what's happening on that one. The whole thing's 9, and it's split into thirds. And the 2/3 part is 6, and the 1/3 part is 3. So it's a 3, a 6, and a whole thing 9. All right, what if it was really ugly numbers? Could y'all do it? Like, for example, what if I tell you that this is a median and this is a median? So that's a centroid, right? And what if I tell you that this whole thing right here, let's call it AB. What if I tell you that AB is 11? Gross, right? Because I've got to take that whole thing 11 and divide it into thirds, right? So the big number is 11. Well, here's the easiest way to do it. Okay, y'all listening? A third of 11, right? That's what I need. I need to divide 11 into thirds. So isn't it 11 thirds, 11 thirds, 11 thirds? Right? So that's how it divides into thirds. So let me explain what I did. When you add fractions, you know how you only add the tops? So 11 plus 11 plus 11 is 33 thirds. So this is just 11 split into thirds. It's 11 thirds, 11 thirds, and 11 thirds. 2 of those is the longer one. So the longer one is 22 thirds. And the shorter one is 11 thirds. Now, if you hate fractions, you can change those. You could change that to 7 1/3 and 3 1/3. Right? No, 3 2/3. Sorry. So this is 3 2/3, and this is 7 1/3. But I just leave them fractions. All right. So what if I tell you that this one is 15? No, not 15. That was too pretty. 26.
44 1/2.
Okay, now that's just really gross. We'll do 26. So suppose I tell you the whole thing's 26. So we've got 26 thirds, 26 thirds, and 26 thirds. Oops. So this one would be 52 thirds. 52 thirds. And this one would be 26 thirds. So you just take whatever the whole thing is and divide it by 3, and 2 of them is the longer one, and 1 of them is the shorter one. So you could do it with ugly numbers. It's just ugly.
Could you do it if it was a square root of pi?
Sure, it'd be square root of pi thirds, square root of pi thirds, square root of pi thirds,
Oh.
and then two of them would be 2 square root of 3 pi. No, 2 square root of pi thirds. Anyway, yes, you could. Question.
These triangles would have to be to scale, right?
So you're asking, would they draw them to scale, or would they automatically land to scale? Is that what you're asking?
If like the triangles could be not to scale on the test.
Yes, but that's a complicated question to answer. So good question, but complicated. So I can make the triangle whatever size I want, right? If I draw a median in there, there's nothing I could do to mess with that 2/3, 1/3 relationship. Like, I can't make it look any different than it is because it's the shape of a triangle, and the shape of the triangle didn't change. So if I draw a true median, and if I draw another true median, then there's nothing I can do about that's 2/3 and that's 1/3. Like the scale, it's gonna be 2/3, 1/3. It's gonna be split that way. And I can't mess that up. Now, the only way I could mess it up, so I just kind of messed up what I just said. But anyway, I could make it inaccurate looking if I didn't actually make that a true median. So like if I wasn't careful in drawing this and this truly wasn't a midpoint, then it would mess up that it's 2/3, 1/3 because I'm not being accurate with my drawing. So I guess to answer that question, I'll say this. When people write questions for a test, it's possible that they could be a little inaccurate in the drawing and it's not a true median. And if it's not a true median, then it won't truly be divided 2/3, 1/3. But if it really is actually a median, like it actually is one, then it will have the 2/3, 1/3 relationship. I don't know if I answered that well, but that's the answer. Okay, I want you guys to do the rest of these. So you guys do 4 through 13, and